Now that we've talked about the concept of an average representing some kind of statistic within our population, we want to talk about a couple other things. So these measures of average are really good tools to help us start analyzing data, but the problem is that doesn't really give you a clear picture of what's going on. So we wanted to kind of talk about how spread out our data values are. So we need something that represents the typical person or thing in that population, but we also want to see, is our data close to this value? Is it really widespread? What's going on? So we have two things to do this, one of which we've already seen. So the range and the standard deviation give us an idea of how spread out the data is. Okay. The range is something we've already seen. It's the difference in the highest and the lowest values. The standard deviation is going to be a little bit more complicated. There's a lot more to it. And so if you're going on to statistics, this is something you're going to use pretty heavily. So we want to put a good focus on this. So standard deviation measures the average distance of the data values to the mean. So you have all of your data, you have this number that's representing the average, and it should be somewhere in the middle. And we want to see, is our data close by? Is it far apart? So the standard deviation will do this. It's represented by the Greek letter sigma. And so just like when we talk about the mean, we use that X bar. What we're going to do for sigma is we have the Greek letter that looks like this. So if we're asked to find the standard deviation, we're looking for sigma. Okay. Now, depending on the value of the standard deviation, it's going to tell you information about where your data is lying. So if you have your average and you have a very large value for the sigma in comparison to the mean itself, this means there's going to be a lot of data that's far from that mean. However, if you have a small sigma value, that means that most of your data is going to be nearby to the mean. So there's not too many outliers in this instance. So when we're going through and we're calculating the standard deviation, we've got a process that we have to follow. So the very first thing we need to do is we need to find that mean of the data set. So remember, that means we're going to add everything up, divide by however many values we've added together. Now what I want to do is I want to find the distance to the mean. So the second step is going to do exactly that. We subtract the mean from each data value. So it gives us the distance to that mean. So just to kind of show you an example, if our mean is 75 and then I have another value 72, when I subtract them, that gives me a distance of 3, okay? And the thing is, I'm not really going to care about positive or negative values because that just tells me which side it lies on. But when I'm looking for a distance is a positive number. So to combat that, we've got to kind of work with a little bit of some trickery, I guess you could call it. But what happens is, in some instances, you're going to have positive values because your data value is larger than the mean. But if your data value is smaller, you're going to have negative values. So this step is going to give you a combination of positive and negative values. And I want to find the average of the distance, so I don't want to deal with these negative signs. So what this third step does is it's going to square those values from the prior one. So once I get the distance from each data value to the mean, I square it to make it a positive number. Then I'm going to go ahead and average those values together. So I've got my square differences, I'm going to add them all up, and I'm going to divide by however many square differences this is. So this gives me the average of the square of the distance. So we haven't talked about a square root, but that's what this final step does. So we're going to find the square root of this average from step 4. Because we squared all of the distances, the square root is going to undo that. So you're going to have in your calculator a little button that you'll see that looks just like this. Once you get the number, you're going to input that and then hit your square root button. And again, it'll be dependent upon your calculator, but to show you an example, if you're using your phone, you're going to have a square root button right here. So in this case, if I want to say, if I added all of my differences together and it turned out, and divided it by the number of values and it turned out to be 10, on my calculator I would do 10 and then I would press this button. And so my standard deviation would be about 3.2, okay? So let's try an example together. Again, this is a process that's going to take a bit of time, so we're going to break it down piece by piece. So suppose we score these values on 6 different exams in your class. We're going to start by finding one measure of our spread, which is our range. So what I need to do is I need to look at my highest value, which in this case, my highest score was an 81, and then my smallest score, which is a 72. So my range is just the difference in these values. 81 minus 72, giving us a range of 9. Okay? So that just tells us the difference in the highest and lowest values. Now we want to calculate the standard deviation. So again, I'm going to follow this step by step. Very first thing I need to do is I need to find the mean of this data set. So I've got 6 tests. I want to add these 6 tests together, and then I'm going to divide by how many tests there are, which is 6. So our mean is going to be 75 plus 80 plus 72 plus 81 plus 75 plus 77, and then all of that divided by 6. So if you add these together, it's going to give you 460. And then when you divide that by 6, we're going to have to round because it's not a nice number. It's about equal to 76.7. So our mean test score is 76.7. So what I want to do now is I want to find what is the distance from the mean to each and every single one of these data values. So I'm going to subtract the mean from every single value. So our first data value is 75, and I subtract the mean, which is 76.7. And when you do that, you get negative 1.7. Our second data value is 80, subtract the mean, and this gives us 3.3. Third value is 72. We need to subtract the mean, and so the distance is negative 4.7. Fourth value, 81, minus 76.7 gives us positive 4.3. Then we've got 75, subtract the mean, and it gives us negative 1.7. And last but not least, we have 77 minus the mean, giving us a really small value of 0.7. So this gives me the distance from each data value to the mean. So what I want to do now, again, some of these values are positive and negative, so I don't want to average these. I want to make them so they're all in the same playing field. We're going to square these values. So every single value I'm going to square, which just means you're taking that number and multiplying it by itself. Because when you take a negative times a negative, it gives you a positive. So negative 1.7 squared gives us 2.89. The next distance was positive 3.3. When you square it, that's 10.89. Next distance, negative 4.7, and squared gives you 22.09. Fourth distance is 4.3. And squaring that is 18.49. Next distance is negative 1.7, and squared will be positive 2.89 again. Then we've got 0.3 squared, which gives us 0.09. Okay. So again, it made everything on the same playing field so that all of those distances now became positive values. And so what I'm doing in this fourth step is I'm averaging the square differences. So we're averaging all of these values. So we're finding the mean. So I want to take all of these values together, add them up, and then I'm going to divide by 6 because I have 6 values. So if I add everything in the numerator, it's 57.34. Divide that by 6, and it gives us 9.56. Okay. So again, this gives me the average square distance. So what I want to do to find my standard deviation is I take the square root of this number. So our value of sigma, the standard deviation, is the square root of 9.56. So again, going back to my calculator, I've got 9.56. I want to take the square root of that. And so we'll go out to 2 decimal places. Our standard deviation is 3.09. So it's about equal to 3.09. Okay. So this number is small in comparison to our mean, because our mean was 76.7. So that tells me most of my data values lie around the mean. If I had scored, say, a 10 on a test, that tells you we have quite a big outlier. So my standard deviation would be a lot higher because I have data values that are far from the average. But this small number in comparison to that mean is telling me that things are pretty close to each other. Okay? So what's going to happen a lot of times is you're going to hear another word that's often associated with this. So one thing that appears really frequently when you have any kind of data set is when you go to plot the histogram associated to it, you're going to see a really common shape. So if you look at these 2 pictures, this is SAT scores. It has a very similar shape, and most of your information is lying right around that 1,150 test score on those 2 components. And same thing here. Most of your data is right in that center, and then it kind of tapers off. So these are roughly symmetric to each other. So when we have this shape, this is actually called a bell curve because it looks kind of like a bell. Okay? So when you have a data set that has a pattern like this in its histogram, we say the data is normally distributed. Because most data sets are going to have this. This is the average SAT score. And then people score pretty evenly on either side of that. You have way less people that are getting a perfect score of 1,600, and you have way less people that are on the other end of the spectrum too. So most people fall within a certain range, and you can see most of your data is really lying in between some certain values. Okay, so most things in life, if you look at like women's height, women's weight, men's height, men's weight, IQ, all of these are going to have a bell curve when you go to plot that histogram. So these are normally distributed data. When you think of the word normally, it's average. It's what you would expect to happen. So a lot of data occurs with this. So the really nice thing about these normal distributions is this point that's right in the middle is actually going to be your mean. So the mean is going to be the center because that is your best representation for that population. And then the standard deviation is actually going to tell you a lot of information about where your data falls. So this is what we call the empirical rule. The empirical rule tells us how data falls within certain ranges and around the mean. So first and foremost, just to make my typo here, if you look at your data, 68% of all of the values will fall within one standard deviation of the mean. So what I'm actually going to do is I'm going to give you a little chart to kind of show you what this represents. So here's our mean in the very center. It's where most of your data should be. If I add one standard deviation or subtract one standard deviation, between these 2 values should lie 65% of your information. Now, if I go out to 2 standard deviations, meaning I add a second standard deviation over here. So really the distance from here to here is 2 of that sigma value. Or if I subtract 2 sigmas, then 95% of your data should lie within these 2 values. So from here to here will be 95% of the values. And then last but not least, if I go out a distance of 3 sigma on either side, 99.7% of your data is going to lie within that range. So whatever these values end up being, 99.7% of all of your data values will fall in here. So everything is pretty centered around that mean. Okay. So let's try a couple examples. On the first one, we're told on a nationwide test taken by high school students, the mean score is 53 and the standard deviation was 11. The scores were normally distributed. We want to figure out approximately what percent of students scored between the range of 20 and 86. So essentially what I need to figure out here, because I know these scores are normally distributed, my mean is 53, I'm trying to figure out how many standard deviations away are these 2 values. Okay. So if I start at my mean of 53 and I add 1 standard deviation, that would be 64. Add another standard deviation would get me to 75. And add 1 more standard deviation, I end up with that upper value, 86. And then in the same way, if I subtract 1 standard deviation, that's going to get me to 42. Another standard deviation is 33 or 31. Another standard deviation away lands me to 20, and it gives me the lower bound. So we are 3 standard deviations away from the mean on both sides. So using our empirical rule, because I'm 3 standard deviations away, 99.7% of students would have scored between these 2 values. So 99.7% of students scored between 20 and 86. Okay. So we're basically just trying to see again, how many standard deviations away are we? Now, if I'm instead asking approximately 95% of students scored between what values, now I'm doing the opposite. I want to figure out what is the range. So if I'm dealing with 95%, that should be 2 standard deviations on either side. So we need to figure out 95% falls within 2 sigmas. So we need to figure out the upper and lower bound. So one way I'm going to do that is I'm going to add 2 standard deviations. This gives me my upper bound of 75. And then if I subtract 2 standard deviations, that gives me my lower bound of 31. So my range, so that 95% of students fall within, so 95% of students scored between 31 and 75. So it gives you the upper and lower values of the range. Okay. So let's try one more. We're told the length of movie files are normally distributed with a mean of 190.3 minutes and a standard deviation of 19.8 minutes. We want to use the empirical rule to fill in the pieces. So you'll have a nice little drop down in your chart. But what I want to do is I want to fill in what these numbers are, okay? So you can see we've got this bell curve going on. And because it's a bell curve, that tells me this number that's directly in the middle should be my mean. And we're also using the scale down here. This number should be something in between 180 and 200. So my mean is going to go right there. The number that we should fill in will be 190.3. Okay. Now, before I can answer what the percentage of this shaded area is, I really need to figure out what are these two values and how many standard deviations away are we. So what I'm going to do is I'm going to start with that mean, and I'm going to go ahead and I'm going to add 1 sigma and see, does that get me to a number between 220 and 240. So if I do that, if I take my mean and add the standard deviation of 19.8, that gives me 210.1. But that's actually somewhere here in between 200 and 220. So 1 standard deviation did not get me to this value. So if I add a second to this, that gets me to 229.9. And that is a number that's roughly halfway in between 220 and 240. So the number we should fill in here should be 229.9, okay, which is 2 standard deviations from the mean. And now I want to make sure, does this other number fall into that same pattern that it's 2 standard deviations away? So same process, I'm going to start with the mean, but since it's on the left, I'm going to subtract my standard deviation of 19.8. So that would give me 170.5. But that's a number that's in between 160 and 180. So not 1 standard deviation away. Going 1 more step, subtracting 19.8 gives me 150.7. And that seems like a plausible number between these two values. So that is halfway in between roughly 140 and 160. So again, this one is also 2 sigmas from the mean. Okay. So this shaded region between these two endpoints is 2 standard deviations along each side. That tells me that 95% of my data should be within this total shaded region. Okay. So again, just using that empirical rule.